Okay. I happen to be at my office at Seek, and somehow I have three. Oops. With three screens, I can't quite tell where my cursor is going to be. Come on. Get on over there. There it is. Okay. Okay. So today we'll mostly. I'll come back to the exam here in a second. So today, we'll keep talking about moment of momentum after we get done going through the exam. One announcement: the final will be on Sunday, May 2nd, from 4:30 to 7 p.m. So please let me know if you have more than two exams scheduled for that day, and we may need to make alternative arrangements. Homework 10 is posted, and that's due on Thursday before class. With respect to the exam, real quick, I'm really close to getting these finished as far as grading goes. So we will get the grades posted as soon as possible. It'll probably be tomorrow morning, realistically, because I want to kind of sit back and look at the distribution of grades and sort of figure out where everything lies. But I can't do that until everything's finished with grading. And Alexia and Emma have done a great job on their parts of the grading, and I'm the one who's a little bit behind. So I expect to get all those done today, tonight, and then we'll let you know, and we will release the grades at that point. Systematically, I think there were two small errors that I will point out to you. One of them, actually, I can't point out because it's in the solution. So remember, problems 1 through 10, I didn't find any problems with necessarily in grading them or during the exam. Nobody asked, "Hey, what's going on here?" But when we get to 11 through 15, there was one where I had one little square a little bit wrong, and then there was another one where I had entered the wrong number for the solution, but that's okay. I had done something wrong in my calculations, but in any event, I'm going through and checking that on every person's exam, so not to worry if it was marked wrong. Like, I'm going through and going, okay, that's the right number. I'm giving you 5 points, but I'm not necessarily making a comment. So in other words, if you go back in after you look at the exam and you go, hey, wait a minute, I got 5 points for this, and that number is completely different than the number that is the solution, don't worry about it. That's because it was an error in the solution. I'm reticent to go and change the solution in or the solutions, because there were 5 different versions of each of the questions, just because I don't trust Canvas. So trust your grade. But if you do have any questions about your grade, of course, reach out. Both Emma and I will have regular office hours tomorrow. I don't know that we will get the grades released before Emma's office hours, so it might be mine that you come to in the afternoon, which is totally fine. We're planning to have regular office hours, so I'm happy to answer any questions. What else with respect to the grades? I can't tell you anything about a curve or anything, just because we don't have them all finalized, so I haven't looked at the total distribution. Aside from that, I can't think of anything else. Emma or Alexi, did anything pop up in the chat? We're good? Okay. Then I'll just move along here. Okay. Let's see. Well, this kind of works, except I need to, come on now. What happened here? This is weird. Now I can't write on this. What happened? Okay, let me try one thing. Oh, there we go. Okay. All right, I'm going to go with blue today. All right. So I'm just going to go through these 18 problems. Remember, you would have only had 10 of them. I can't predict exactly which 10 you had, so I'm just going to go through all of them and you'll have the benefit then of having the ones answered that you had at some point along the way. I'd say most of these, there wasn't a big problem. One of the issues with respect to, let me do this one first in the middle and the second one. These were two different questions, but they had the same graphic with them. The acceleration of a particle is given by the following equation. So this one, the term in dashed outline number 1, so this one right here, is termed as the local acceleration. Now, one thing to note, if you typed into the word box local acceleration, like that full term, it came up as wrong because all I was looking for was local since acceleration was there. So I went through and just made sure that the things that were wrong were actually wrong, and which means that if you had typed local acceleration, hopefully I caught it and gave you the points back. But that's one of the things to check in your exam, to just make sure that those are correct. So I'm checking through these top 10 and then moving on to the other calculation ones, but just as a note. And then a separate question was, again with the same graphic, if the acceleration of a particle is given by the following equation, and the term dashed outline 2, so this one, is termed the convective acceleration. Okay. I think I saw one misspelling of this. That would have been another problem that Canvas would have had. It would not have liked the misspelling. So again, I'm trying to check those, but if I miss something, please by all means ask, and we can sit down and go through your answers and figure out whether they merit points or not, if I missed it. And then going back to the first one here, when applying the Bernoulli equation, Christian, do you have any question?
Oh, sorry.
Oh, okay. All right. When applying the Bernoulli equation, we often choose a stagnation point as one location of evaluation of the total energy, because we can assume that the velocity ahead at this point is, the correct answer to this was 0, right? Or you could have typed out 0. I think, I'm trying to remember, I think both of those were values that I had put in as correct answers. Some of you also put constant, and that's not the same as 0, but I might have given you 1 out of 2 points for that, something along that line. So just note that as it comes along. All right, true false question. There were 4 of these total. These are the first 2. The next 2 are on the next slide. Under conservation of mass, the time rate of change of mass of the coincidence system. So this is the time rate of change of the mass of the coincidence system is this piece right here, right? Those are the words that describe the left-hand side of this equation. This is the same equation we've been looking at for the past couple of weeks, is equal to the net rate of flow of mass, flow of mass through the control surface, which is this piece right here. So under the conservation of mass, we don't expect any change with time. So this would end up being a true statement only because you would expect that there's no change in density with time, no change in storage, so that would be assumed to be 0, okay? So I think most of you got that right. If you were having if there's some systematic problem I'm not picking up on, by all means, let me know, and we can talk that through. One approach to using the Bernoulli equation is to have all energy terms in dimensions of force. And I put the F there as a dimension, not as like the answer is false. So it turns out that the answer is actually false for this one. Remember that we can write this in terms of pressure, which we have right here. And we can also write it in terms of head. And the head version is Z plus P over gamma plus V squared over 2g, right? That's the head version. This is the pressure version. Those are constant along streamlines in either case, just 2 different versions of the Bernoulli equation, where the translation between the 2 is basically just divided through by gamma, right? If you divide rho by gamma, you'd get rho over, pressure divided by gamma, you get pressure over gamma. If you divide gamma times z by gamma, you just get z, and 1/2 rho v squared divided by gamma would give you v squared over 2g, right? Because gamma is rho times g. So that one is false. Force is not a way in which we represent the Bernoulli equation or the energy terms in the Bernoulli equation. The energy line is as high or higher than the hydraulic grade line. This was meant to be in a visual sense, so I didn't give you an image. This was an image from another problem that I'll show in a second, but I just wanted to give you this image to identify this. The hydraulic grade line is this one right here, and it goes down here and out. The energy line is the top one up there that's going across that's horizontal. So that's this guy right here. It's kind of getting interrupted by this. Okay, so we go across. So there's the energy line. And so the energy line, remember, represents the sum of all three energy types. So it's E is the potential energy, C in this case is the pressure energy, and B is the velocity head. And so the difference between the HGL and the EL, the hydraulic grade line and the energy line, is always the velocity head. Okay, therefore it always has to be coincident with, which is what it is here, and where velocity is zero essentially is where you're going to have these two be the same. But the energy line should never dip below the hydraulic grade line essentially. So this one is true as well. I guess thinking through this a little bit, I suppose you could have a negative velocity. I didn't think through that, but anyway, in most systems, this should end up being true. If one were filling or draining a reservoir or pond and a control volume was defined surrounding the full extent of the water body, the time rate of change of the mass, so time rate of change of the mass of the contents of the control volume would not be equal to zero. And that's true because essentially what this is saying is that control volume drawn around a reservoir, the reservoir can rise and fall, right? So it's unlike, I was trying to get at the distinction between a reservoir, which is open to the atmosphere, can rise and fall, and, a pipe bend or something else that we might draw a control volume around that can't change its size, right? That storage is fixed. Once it's full, it's full. Anything that comes in has to push out the same amount of mass and volume on the other side. And in this case with the reservoir, of course, that's not true. You can take in more than goes out, and you can let out more than comes in at any one moment as well. Okay? Okay, there were two different questions that included this graphic, which I just showed you previously, but now we specifically look at the answers to this were basically A through G. And so the question is, the first question was, which letter represents the hydraulic grade line? And the hydraulic grade line, again, is this one right here. And so the only one that's really identifying that particular line is D. And then which letter represents the velocity head at point 2? Okay, so here's point 2, and remember the velocity head is the difference between the hydraulic grade line and the energy line, so it turns out that is B in this case. Okay, so that's the indication there. I got a couple of folks that seemed there was a common desire to use G, but that's not a point 2, that would be a point 3. So I'm not quite sure if there was just a problem identifying where point 2 was or not, but in any event, 2 was indicated to be in the larger diameter part of the pipe out of this reservoir. Okay, this was the graphic that went along with this particular question. The format may look a little bit different. These are the same answers. I think I took out all the quotation marks you may have seen. So a general version of the material derivative is shown below, where B is an extensive property of the fluid, so it's mass, temperature, velocity, etc. And A and B are placeholders in the subscript, so that's just here and here. Which of the following is correct? A is out, B is in. So in other words, this would be out, and this would be an in subscript, or A is in and B is out, or should A be cis and B is CV, or is A velocity and B is acceleration. Okay, so it turns out, and this just gets back to that fundamental issue that we talked about, where this is derived from that n hat, that normal vector that's always normal, or it's a unit vector always normal to the control surface. Therefore, your outs are added and your ins are subtracted. So this A version, or rather this version, was the correct answer on that one. Okay, so that was just kind of getting back to the fundamentals of using that the material derivative, which we eventually used to start to define the Reynolds transport theorem, which we'll do in the next slide. Okay, on the next slide here, then we have this question: which term in the Reynolds transport theorem represents the net rate of flow of mass through the control surface? So part of this is given away by using the term control surface. Remember, sys refers to the system, CV is control volume, the control surface is defined here. This is term 3 because remember, this is also that normal unit vector around the entire control surface. So term 3 was the correct answer there. All right. So that's the right one for the rate of flow rate of mass through the control surface. This one's slightly different than now. Which term in the Reynolds transport theorem represents the time rate of change of mass of the coincident system? So in this case, now we're focusing on system, and so in this case, it's term number 1. If we had said something about the control volume, the sort of storage of mass in the control volume, that would be term number 2. But in this case, we're focused on the system, and so we're using this is indicating term 1. All right, air flows through a doorway at an angle alpha shown in the figure. Which is the correct expression for the mass flow rate, the m dot term? I couldn't put an actual m with a dot on it in Canvas, so I used m dash dot. So I hope that was not unclear. The mass flow rate of air through the doorway. Now, what we mean by this is that if we were to apply the Reynolds transport theorem, remember that, let me change the color of my pen here. Remember that we need to look at normal fluxes, that is, fluxes that are perpendicular. So even though this is at some angle alpha from the wall, this in or out flux, I guess we don't know whether it's going in or out, what our frame of reference is. But regardless, what we're going to need is the normal component. So think about this vector as having that direction and that direction. And so given alpha, well, we care about this component right here, which means that we would look at rho times A times V, and then we would only really be looking at the sine of alpha. In other words, the normal component, the component that is perpendicular to the doorway. And that's where the trig comes in here, is that it's not just rho times A times V, because we have this going at an angle, we need to look at the perpendicular component to that. Okay, you were given this graphic. Again, I had to kind of make these graphics in like PowerPoint, do a screen capture, and then upload that screen capture as an image to Canvas. But you're given minus 23i, a velocity vector of minus 23i plus 127j plus 0k. Because this is 0k, we can basically say there's nothing going on in that z direction, right? Therefore, this ends up just being a two-dimensional velocity vector, right? I mean, we show the k, but because it's 0, this ends up being a two-dimensional flow, essentially a two-dimensional velocity. Okay, the pressure version of the Bernoulli equation is noted below. Which term represents the static pressures? So now we were sort of focusing in on just a couple of these terms that we had used to define things like static pressure, and the next one is stagnation pressure. In this case, it turns out to be just term number 1 here. So the static pressure is denoted as that P value in this version of the Bernoulli equation. And then the stagnation pressure, in the next slide, remember, is the one that we used for that stagnation point right in front of a manometer that's coming out into the flow. And so in this case, it's actually both of these terms summed together. So term 1 and 2 make up what we call the stagnation pressure, because you've got some amount of the velocity head acting against, or velocity energy. In this case, it's represented as a pressure, not a head, but this pressure that is pushing against that opening to that manometer. Okay, so that stagnation point has these two acting to push water up that manometer, or whatever the fluid is. Okay, water flows without friction through a horizontal pipe that enters a section where the cross-sectional area is small. So here's point number 1, here's some point number 2, right? The velocity profile is uniform in sections 1 and 2. The correct statement about the static pressure P P2 relative to P1, and velocity V2 relative to V1 along the streamline down the center of the pipe is what? Okay, so before we go through these, let's note that given that gravity is downward, Z1 we expect is equal to Z2, right? So if we think about this in terms of Bernoulli, I'll just write out the equation: Z1 plus P1 over gamma plus V1 squared over 2G is going to be equal to Z2 plus P2 over gamma plus V2 squared over 2G. Okay, so we know that Z1 and Z2 are basically the same, so they'll cancel out on either side of this, which means that if velocity changes, so if velocity decreases from point 1 to point 2, then pressure has to increase, right? These two are sort of offsetting each other. So a decrease from V1 to V2 means an increase from P1 to P2, and vice versa. Okay, so how are V1 and V2 related? In this case, this is a larger cross section than this one at point 1. Therefore, so if A1 is greater than A2, then we know that V1 has to be less than V2. All right, right from just Q1 equals Q2. We're lumping in a little bit of the continuity equation here, and therefore the pressure. So for V1 being less than V2, we can ignore this one and we can ignore that one. So now, what happens with pressure? So if velocity increases from 1 to 2, then pressure has to decrease from 1 to 2. Okay? So V1 is less than V2, P1 is greater than P2. That's the correct answer here. Okay? So we can reason through just the relative amounts of these without getting into specific numbers, simply because we can sort of estimate what these relative changes are in the system. All right, in the figure below, water flows through this constriction, got my R there, through this constriction. At which location is the velocity the greatest and the pressure the least? Well, we don't quite know, let's just say A1 here is greater than A2, which is less than A3, right? And so for the same amount of discharge Q moving through this, in this case we're told it's water, but as long as it's an incompressible fluid, we would expect that V1 is less than V2, which is less than V3, right? We don't really care about the difference between 1 and 3. We just, sorry, I goofed that up. This should be V2 is greater than V3. We don't know how 1 and 3 relate to each other, but in this case, we see that point number 2 has to be the greatest velocity, simply because it has to increase from 1 to 2, and then from 2 to 3, when we work our way back out from small to large cross-sectional area, of course, velocity has to drop from 2 to 3. So the greatest velocity is the greatest has to be point number 2. Now, we also said where is pressure the least? That kind of goes back to the previous example where if we assumed all of these are the same z value, we could reasonably come to the conclusion that pressure must be the least where the velocity is the greatest. Okay, so we could take that a step further, but really just the velocity being the greatest among these 3 points is enough for us to be able to answer this question. Okay, so that covers the multiple choice, true, false, fill in the blank types of questions from the first part of the exam. Again, that was 20% of the exam overall. And then this section is 30%, and all of you had some version of this problem where I hope this wasn't too confusing. I did get a couple of questions on it, but it was meant to be sort of a 2-part question where the first part is just using the Bernoulli equation to figure out the velocity of the water exiting the pipe back into the reservoir, and then the second part was to determine the diameter of the supply pipe that meets this requirement. So in other words, using the continuity equation to size the pipe more or less correctly. So assume the water tower, this water tower has one pipe going from its base to the tank, thus it can either fill or drain. When the water tower is half full, the free surface is 95 feet above the reservoir surface. The design specifications require that when the tank is half full, it can be drained back to supply at a flow rate of 2,210 cubic feet per minute. Assume that water flows freely at the end of the pipe into the surface of the reservoir. So I was trying to be careful not to invoke the jet idea necessarily. It turns out that equation would have worked, but I also was trying not to confuse you and make you think that the pipe went down into the reservoir and was submerged somewhere. So the idea was it just comes out at this elevation. You can consider that 0 compared to the 95 feet at the top of the water surface. If losses are neglected, what diameter must supply the pipe? Must the supply pipe exceed to meet this requirement? Assuming that the pressure inside the tank is the same as atmospheric, and that the diameter of the tank is much larger than that of the supply or drain pipe. So we can answer this in 2 steps. So the idea was that with terms like the diameter of the tank is much larger than that of the pipe, the idea means that would suggest that if this is point number 1 and this is point number 2, that V1 is equal to 0. Equal to 0. And then we also note the pressure inside the tank is the same as atmospheric. That means that P1 is also equal to 0. And then, of course, we are shooting back into the atmosphere, this water at the end of the pipe here. So P2 is going to be equal to 0 as well, right? So that's some simplification. We also can assume that Z2 is equal to 0, and Z1 then is defined by the problem to be 95 feet in this case. So your numbers may have been different, but you go through the same process. So we have a Z offset. We don't know what V2 is. We can solve for that with Bernoulli equation. We'll do that on the next slide. And then we can go back to basically Q. We're given a volumetric flow rate that we can figure out what the cross-sectional area needs to be to have the velocity that we figure out in part A. So part A, then, we apply the Bernoulli equation. That was not a Z. Z1 plus P1 over gamma plus V1 squared over 2G is equal to Z2 plus P2 over gamma plus V2 squared over 2G. 2G. Okay, so we said P2 is 0, we said P1 is 0, we said V1 is 0, and Z2 is equal to 0. Z1 is our 95, I think we said 0.0. Yeah, 0.0 feet is equal to now V2 squared over 2G. And so this looks a lot like the free jet equation. So V2 is going to be equal to 2 times, we're working in, well, okay, I'll put 95 feet first. And then we need to multiply by G, and G in feet is 32.2 feet per second squared, right? And we're going to take the square root of all of this. And when you do that math, you should come up with 78.2 feet per second. Okay, so that's just a relationship based on energy. So to be able to, so now the question is, all right, if that's the energy from just taking 95 feet of potential energy and converting it to kinetic energy, then, so this is part A. Part B is what's the pipe diameter we need? So Q, of course, is equal to V times A and we're told that this can go out at 2,210 cubic feet per minute. So the question then is, what diameter do we need? So this is equal to 78.2 feet per second times pi over 4, and then times the diameter of the pipe squared, right? So we can solve for D as being equal to 2210 feet cubed per minute divided by, let's see, I need to do my conversion there. So do I? Yeah, I think I will. Because my velocity is in feet per second here. So this is 1 minute is equal to 60 seconds. And then we divide by 78.2 feet per second. And then over here, I'm just going to multiply by the inverse of that ratio, 4 over pi. I take the square root of this whole thing, and that comes out to be 0.774 feet. Okay? So, let's see here real quick. All right, I think I'm confident of that. When I look at my significant figures real quick, let's go back to what we were given. We've got three, and that's about it. So we should have 3 significant figures here, we do, and we have 3 significant figures here as well, okay? Were there questions that popped up there? I saw something moving in the chat.
It was just about how if people got different heights for the same question.
Oh, right. There were 5 different heights. So this is just the process you go through. Yeah. So you can come back to this when you get to your exam if you want to look at how you solved it versus the way it should be solved. Okay. Here's the one error that I had. This should have been meters per second squared. So my apologies for that instead of meters squared per second. So this should have been meters per second squared. It doesn't change your answer all that much in that basically remember that what you're being asked for here is you're given 2 velocities noted below, compute the average local acceleration through this section. So the average local acceleration is basically figuring out the acceleration at 1 and the acceleration at 2 and taking the average of those 2. Okay, so in this case, A1 is equal to dV1 dt. And again, there were 5 different versions of this, so you may have had different numbers, but this would be d dt of 0.35 t. So that equals just 0.35. And Acceleration number 2 is just that simple as well. V2 dt is equal to ddt of 0.70 t. So that comes out to be 0.70. Goodness. Okay. So we're just going to take the average of these two. So this is 0.35 plus 0. Apologies, I sort of dropped the units. I didn't keep the units in here, but because it was meters per second, this comes out to be meters per second squared, right? And this should also be meters per second squared when we've looked at the temporal derivative of these two. So 0.035 plus 0.70. This, of course, is in meters per second. Units divided by 2. We come up with a value of 0.53. Squared, meters per second squared. Okay? So that was just meant to kind of quiz your notion of how acceleration is related to velocity. And then in this case, you just had to take the average of those two values, these two ends of this particular little constriction. Okay. Oops, that was my workspace for that one. All right, next short calculation. It takes you 1 minute to fill your car's tank with 9 gallons of gasoline. So we can think about that as a flow rate. Q is equal to volume, 9 gallons, divided by a rate of 1 minute, or I'm just going to put this in terms of 60 seconds because I sort of expect I'm going to have to work in seconds. So gallons per second, we don't always use that often. So we could convert that maybe to cubic feet. That's usually a little more useful to us. And so 1 cubic foot is equal to, oops, oh, come on now. 1 foot cubed is equivalent to 7.48 gallons. So then this comes out to be 0.0200 feet cubed per second. Okay, so I actually am not quite sure exactly where we're going here, but I sort of started with recognizing that we've been given a time and a volume, and so I can come up with a flow rate. All right, what is the average mass flux of gasoline leaving the 0.600 inch diameter nozzle at this pump in slugs per second? Assume that the density of gasoline is 1.32 slugs per cubic foot. Okay. This is basically what is m dot. And we know that m dot in general is rho times Q. So in this case, we call it rho gas times Q gas, right? So this was the Q gasoline. We now have this in cubic feet per second. So I've got that. And now I've been given the density of the gasoline. So I can simply write this as 1.32 slugs per foot cubed times 0.0200 feet cubed per second. And when I multiply these two together, I end up with 0.0265 slugs per second. Right, because the cubic feet will cancel, and there's my m dot. Okay, so there's my mass flow rate as we looked at a number of times before. So in part, this one was really just getting at this equation, and then that was repeated a couple of times actually throughout the rest of the exam, and then just figuring out how you get, is it A times V to get Q, or what else, whatever you need to try to make this work out. Okay. Next short calculation is this question about This is one that you saw in the homework a little bit differently. We had talked about, I think it was like a 3 or 4 inch diameter, sort of for a thin walled part of the tubing in this constriction. I reused this in a different way. Most of you had, I think everybody had this 10 centimeter bit, but you didn't necessarily need that in 15. But this is what you really needed. And there were 5 different versions that had 5 different values here. And then the other thing you needed was this pressure drop right here. So water flows steadily with negligible viscous effects through the pipe shown. It is known that the 10 centimeter diameter section of the thin walled tubing will collapse if the pressure within it becomes less than 15.2 pascals below atmospheric pressure. So what is the velocity in this 10 centimeter section, diameter section for this particular condition? Okay, so the way I'm thinking about this is I'm going to put a point number here, point number 1. That's one place where I can start the Bernoulli equation and make things pretty easy for myself. Clearly, I want to use it here as well, right? Point number 2, somewhere in the middle of that constriction. And then the other place that I could apply it is over here at 3, all right? Now, again, 3 would allow us to be simplify things a little bit. Unfortunately, we're not given any information about this H value. So I don't know what the head difference is between these two or the vertical distance. So I should probably stick with 1 to 2. Okay, so I'm going to do that on the next slide. I'm going to write out the full Bernoulli equation and show how we can simplify it to solve this problem. Note that we are given essentially that P2 is equal to, note that this is 15.2 pascals below atmospheric pressure. So if P1 is equal to 0, then P2 is equal to minus 15.2, and a pascal, remember, is newtons per meter squared. Right? So that's going to go into, obviously, our equation as well. All right, so on the next slide, we've got our good old friend Bernoulli here, Z1 plus P1 over gamma plus V1 squared over 2G is equal to Z2 plus P2 over gamma plus V2 squared over 2G. Okay, so for starters, at point number 1, we know that the pressure is 0 because we're at atmospheric at the top of that reservoir on the left. The velocity there should also be equal to 0. And then within, and then it's got some height, right? So Z1 is equal to 2.94 meters here. That's the vertical distance between point 2 and point number 1. So Z1 is 2.94 meters, and that is equal to, and then on the right-hand side, relative to 2.94, yeah, I just want to make sure I got that number right. Z2 is equal to 0. We are given the pressure, so we'll plug that one in here in just a moment. And then we've got, we're actually looking for V2, right? That's our goal here. So this is now equal to a minus 15.2 newtons per meter squared divided by gamma for water is 9810, right? Newtons per meter cubed, plus, and then we add V2 squared, oh boy, that's a V. V2 squared over 2 times 9.81 meters per second squared, right? So we should be able to solve this now. So basically what we get is V2 is equal to 2 times 2.94 meters plus, and if I take this ratio right here, I get 0.00155 meters. Now, why did that become positive? Because it was negative over here. When I move it to the left-hand side to isolate my velocity, of course, it becomes a positive, right? So we've added those two heads together, multiplied by 2. Now I need to multiply by G, 9.81 meters per second squared, the acceleration due to gravity, and then we take the square root of the whole thing. So just one thing I want you to note, look at how small this velocity head is, right? It's not that big. I'm sorry, the pressure head, the negative pressure head, compared to this elevation head. In this case, like that, it doesn't take much negative pressure for that constriction of that material to buckle in the way that it's proven here. So V2 then comes out to be a value of 7.60 meters per second, and note that there's no negative left in this at all. The fact that this was negative on the right-hand side, it moved over to the left, it became an addition, and we're not at some negative velocity or anything like that. Now, one way you could have gone wrong is if you didn't take the square root. If you were in a hurry, it's possible you got a number that is 7.6 times this. I think it's 57 point something, or somewhere in the 50s. So. Okay, any questions on that one?
Looks like you're good.
Great. Okay. Water enters a cylindrical tank through two pipes at rates of, I'm going to call this Q1 is equal to 50.0 cubic feet per minute. And we're given a Q2 as well. These are both inflows, 200 feet cubed per minute. If the level of the water in the tank remains constant, calculate the average velocity of the flow in feet per second leaving the tank through an 8-inch inside diameter pipe. So Q3 is an out, and that's going to be equal to some V3 A3, right? And so the other thing that we know is that Q1 as one inflow plus Q2 as another inflow is equal to Q3 because we said that the level of the water in the tank remains constant. So in other words, there's no change in storage. So Q3 has to equal essentially 250 cubic feet per minute. So I won't bore you with that math, but 250 feet cubed per minute is equal to, now we're being asked for the velocity. So we simply take V3 on the right-hand side, and we divide by A3, so pi over 4, and we're given that the diameter is 8 inches, so 8 over 12 feet, and we take that value and square it. So V3, when we do this math, comes out to be 716.2 feet per minute. Goodness sakes. And so if we then convert that to, we've been asked for feet per second. So if we take that and divide it by 60, we get V3 is also equal to 11.9 feet per second. Okay? So that one's pretty straightforward. Again, mostly making use of the continuity equation. With a density that didn't change, therefore we can just work with the volumes. Okay. The two long calculations. All right. So this one was focused on the Bernoulli equation. The very last one is completely focused on using the we call it the more of the mass flux, mass balance. Okay, so we have water coming out through this hose. It's being siphoned over this hump here. This hump is above the water surface is 2.1 feet, and then the outlet is 3.5 feet below this water surface, the top of that surface. The total depth here is 8.55 feet, and we're asked for a number of things. What is the velocity in the hose? What is the pressure at point 1? What is the pressure at point 2? And what is the pressure at point 3? All right. Note that I've given you the hint here that the pressure at point 3 is less than atmospheric. Now, that means, from a manometry perspective, you might have been tempted to say, well, pressure inside this tube at 3 is the same as the pressure outside, which is going to be 0 at the surface. And the reason it's not, the reason manometry doesn't work here is simply because we have water moving in this tube, right? It's not a static tube. If it was a static tube, then we could come up with that relationship, but it's not static. Okay, the other thing I noted was that at point number 2, we assumed that this is just inside the tubing, which means that if you're inside this tubing, you're not on the outside, then flow is moving, right? There is the same velocity coming out here as there is at this location, right? We're just told that it's a 2-inch diameter hose. We're not given any information about changes. So if it's the same diameter all the way through, then all these velocities, the velocity along the entire length has to be the same. So the velocity in the hose, what do? All right. I decided that I was going to start from point 0 here and go to point number 4, this outflow. Okay, so what I did was I said that, so this is for part A, I said that Z0, so I'm going to apply the Bernoulli equation between point 0 and 4, the surface of the reservoir all the way to the outlet. And you can see that essentially what I'm going to do is come up with a change in my potential head of 3.5 feet that will translate to velocity going from 0 to some velocity at 4, right? So Z0 plus P0 over gamma plus V0 squared over 2G is equal to Z4 plus P4 over gamma plus V4 squared over 2G. And in this case, we of course expect that the velocity at 0 is 0. The pressure at 0 is also equal to 0, but the elevation is 8.55, right? So I'm just going to use the base here as my data. So 8.55 feet is all we're left with on the left-hand side. And on the right-hand side, we now have Z4, which is 8.55 minus 3.5, right? That's the elevation above the datum. And then P4 we said is equal to 0 because we're going out into the atmosphere. And then we have plus V4 squared over 2G. So this is more or less the jet problem again, where we can solve for V4 being equal to, in this case, when we move these to the other side, we're going to get 2 times 32.2 feet per second squared, and then times 3.5 is all that we're left with feet, and then we take the square root of this whole product, and we end up with V4 being equal to 15.0 feet per second. Okay, now real quick, I had three sig figs, 3 sig figs, 3 sig figs. Looks like I've got 3 all the way around, so I can stick with 3 sig figs in my my solution there as well. All right. So we were checking from 11 through the end of through 17, 18. We were checking on sig figs all the way through. Okay.
This is another one where you had different numbers, right?
Yeah. Oh yeah. All of these you could have had different numbers. Yep. Yep. Good question. So there were 5 different versions of each one of these. Okay. B. So now B is, what is the pressure at point 1? Pressure at point 1, this is just going to be hydrostatic. Okay, so but part of the reason that I thought it was important to calculate this is to compare it to what you get at 2, because 2 is just inside this tube where things are moving. They're at the same elevation, more or less, but you'll have 2 different pressure values. So let's take a look at what we get at point number 1, which is what is the pressure at number 1. So pressure at 1 is hydrostatic, so it is simply gamma water times some height h of water above that point. In this case, it's 8.55 feet. So in English terms, we have 62.4 goodness sakes, pounds per foot cubed. and then we multiply by, in this case, 8.55 feet. And we come up with 534 pounds per foot squared. And the other thing I tried to do to just save you guys a little bit of time was ask for all these in pounds per square foot, so you didn't have to do that conversion to PSI, right, pounds per square inch. Okay, so if we're at the bottom of this, we have 534 pounds per square foot of pressure acting. What happens at where P2 occurred? What is P2? All right. So in this case, we can't use hydrostatics because we are inside of this hose and water is moving. So we really need to use the energy equation. Now we could do this in a couple of ways. We could go from 0 to here, or we could go through the tubing and out. So I'm going to choose to apply. Remember, this was 0.4. This was 0.0 up here. I'm going to go from 2 to 4, but you should be able to go, I think you can go from 0 to 2 to get here as well. But in any event, so let's just say apply the Bernoulli equation B dot E dot at 2.2 and 0.4. So Z2 is equal to, plus P2 over gamma plus V2 squared over 2G is equal to Z4 plus P4 over gamma. I wanted that to be squared, my bad. Plus V4 squared, there we go, divided by 2G. Okay, now in part A, we did calculate these velocities. However, as it turns out, so you could plug them in here, but the velocity at point number 2 is going to be the same as at 3, is going to be the same as at 4. So in reality, these just cancel from both sides because they're going to be the exact same value. All right. It also turns out, of course, that P4 is equal to 0 because we're a free jet into the big world. I forgot to put my 2 here, but we're going to solve for P2 here. So P2 is equal to Z4 minus Z2, and we simply multiply by, I guess I'll put it on the back end here, gamma of water. Right, so 62.4. So in this case, what's the difference between these in height? So we have Z2, I guess Z2 we can actually call 0. Sorry, I forgot we were at the bottom for that. So this comes out to be, so this goes to 0 as well. So this comes out to be Z4, which I don't have a height for, so I'm just going to calculate it as 8.55 feet minus 3.5 feet. And when we multiply by 62.4 pounds per foot cubed, I end up with P2 being equal to 315 pounds per foot squared. That is a terrible B. Anyway, that's supposed to be pounds. Okay, so one thing to note, we calculated 534 for the static pressure, and here we have 315. And the reason we have 315 and not 534 is that we've taken some of that pressure energy and converted it over to kinetic energy, right? The moving water through the tube, right? Even though the elevations are basically identical. Okay, part D is just asking us for the pressure at point number 3, and I gave you the hint that in pressure number 3 is less than atmospheric pressure, meaning that it's going to come out to be negative, right? So once again, we can apply Bernoulli equation between 3 and 2, 3 and 4. We can go 3 to 0, 3 to 1 if we want. I'm going to go ahead and apply it from between 3 and 4. And once again, we calculated the velocities, the velocity through this entire hose. And those two velocity heads are going to be identical because it's the same velocity, so they'll cancel out on each side of the equation. Okay, so for part D, we can apply the Bernoulli equation from or at 3 to 4. Okay, so now we have Z3 plus P3 over gamma plus V3 squared over 2G is equal to Z4 plus P4 over gamma, of course, that's equal to 0, plus V4 squared over 2G, and again, V4 and V3 are the same, so those cancel on each side of this equation. So now we can basically calculate that Z3, of course, is equal to 8. Well, we could do this a slightly different way. The difference between 3 and 4, we put 4 back in here on this, and 0 right here, is the difference between 3 and 4. So Z3 minus Z4, of course, is equal to 3.5 feet. So P3 is equal to gamma times Z4 minus Z3, so ultimately minus 3.5 feet. And so we come up with a minus 3.5 times 62.4 pounds per foot squared. I forgot my 0 on that 3.50, or pounds per foot cubed. And we end up with P3 being equal to a negative 218 pounds per foot squared. Okay? Does that make sense? So this whole question was really just focused on how we apply the Bernoulli equation in a couple of different ways. Okay, now the last problem, admittedly, if you recognize this, I guess you consider yourself, with good recognition, because this came from more or less recitation in week 11. This was like the first problem we worked on. And essentially this is all about m.1 being equal to m.2 plus m.3, right? In other words, we have one incoming m dot and two outgoing. m.2 is going out and m.3 is going out as well, okay? So let's just work through these real quick. This is the left-hand side of the Reynolds transport equation. Determine the quantity where this change of the system in time, where the system is carbon tetrachloride contained in the pipe bounded by sections 1, 2, and 3. So in other words, just trying to identify what our control volume would be. And it turns out, from the system perspective, this should always be equal to 0, right? We've said that the left-hand side of this equation, there's no change in mass through time. Our system always keeps the same amount of mass, so A is always going to be 0. Now, then the questions start to get at what is the mass flow rate at section 1? So this is the inflow, so m.1 is equal to rho. I'm just going to use the same rho because it's all carbon tetrachloride, and so I'm not going to label rho 1, but we will have Q1, which of course is equal to A1 times V1. Now we are given here that the velocity at 1 is, the mean velocity is 22.5, the area is 0.5, so this comes out to be 22.5 feet per second times 0.50 feet squared. Wow. Funky feet squared, sorry. And this comes out to be basically 11, What did I do here? Oh, I forgot to include rho. Sorry. Times 3.09. Goodness sakes, that's 3.09 slugs per second. Oh, sorry, slugs per foot cubed. Okay, so this m.1 comes out to be 35. Oh, come on. 35 slugs per second. Okay, so all we did was multiply the area times the velocity times the density. And that's all we were looking for here. Now, part C, we're going to ask what is the mean velocity at section 2, so we can figure that out. And then part D, before we move from here, I just want you to note that we can calculate an M2, determine if possible the value of the integral of this. Basically, this is the exchanges, right, on the right-hand side of this equation. So at section 3. So I just want you to note, we're going to say m.3 is equal to m.1, the inflow, minus m.2, the other outflow, right? So on the next slide, when I do part C and D, just note that part D is going to come from here. Okay, so part C, we are given that the mass flow rate is 10.0 slugs per second at section 2. So that's going to help us because we can now figure out, using this equation at location number 2, we should be able to figure this out. So C m.2, we were given as 10.0 slugs per second, and we know that that is equal to rho times A2 times V2, and we are given that the area 2 is 0.23 feet squared. So we do this down here. So this is equal to 3.09 slugs per foot cube. And then we multiply by area, which is 0.23 feet squared. And then what is V2? That's what we're going to solve for. This is all equal to 10. So V2 comes out to be 14 feet per second. And note that in general, I've got 2 sig figs for this problem. That's my minimum, so I'm sticking with 2 throughout. We have a mix of 2 and 3, so we're going to stick with 2. D, on the other hand, M3, we said, M.3 is equal to M.1, the inflow, minus the other outflow, M.2. And so this comes out to be, we calculated in part B that this was 35 slugs per second. And we were given M2 is 10. So 35 minus 10 is 25. So M.3 is equal to 25 slug per second. Okay? All right. That is that. And it appears as if I don't have time to go through the problem that we were working on yesterday in recitation. So let me break for a second and ask for questions, and then I'll just jump to the participation questions at the very end. Any questions on these? All right. If we're looking good, then we'll jump to participation. So I'll come back and finish that problem on Thursday, first thing. Okay, so rotating lawn sprinkler along with a control volume is shown below. There is no friction force at the surface between the rotating arm and the base, and the air resistance force is 0. The velocity of the water entering the sprinkler is V in, and the relative velocity of the water leaving the sprinkler is W out. The question is, what is the momentum equation for the sprinkler with 0 terms present is which one of these? Is it m dot r naught times W out. So W out is the sprinkler velocity. The relative velocity of the sprinkler is equal to the torque shaft, the shaft torque, or do we need to account for this angular velocity in here at one of these points? And and this one also includes some conservation of momentum, the moment of momentum of the inflowing water as well. So take a look at those and decide which one you think makes the most sense. On my solution here. Oh yeah, right. Okay. All right, we're up to 66. Let's take a look here. How many do we have? 80, so we should get a few more. Let this go for another, I'll go to a minute and a half here. So note that we are spinning one direction and the water is coming out in the other direction. So W out is in an opposite direction of R omega, essentially, the angular velocity. All right, we're up to 73. Let's go ahead and end it there. A minute and a half. Let's see what we have. All right, 9 of you chose A, 11 chose B, 18 chose C, and 35 chose D, and D is the correct answer. This is the right answer because essentially we're looking at this, how does V, or in this case they use W, how does that work? We've got these two going in opposite directions. The relative velocity of the water leaving is opposite the direction of the angular, the direction of turning of the shaft and the arms themselves. Okay, great, looking good. All right, next one looks very similar. Let me reset this. Okay, now we're looking at the relative velocity, but now the momentum equation for the sprinkler looks like this. When we have lawn sprinkler as the control line shown below, the torque is large enough so that the sprinkler arm does not move. So now we're looking for a resisting torque, okay? So let's get this going. I'll let you guys go for a minute and a half here. We might go less than a minute over, so my apologies for that. Now we have V in, and then the relative velocity of the water leaving the sprinkler is W out, but omega is equal to 0. So what do? Which one of these is working for us? Do we subtract? Do we add? Do we subtract? And this is also including the inflowing moment of momentum as well. We're doing that's 79 folks still, so let's go for a minute. A, B, C, or D. $73, it's pretty good. 74. Can we squeeze out a few more? Maybe one more? No? Okay, we'll go to 110. All right, I think that might be all. All right, let's see what we've got. Okay, most of you said A, and it turns out that is actually the correct answer. The reason here is that any of these that included the angular component, omega is 0. So that component would have fallen out essentially, which leaves us with this particular answer. Okay. With that, I will look forward to seeing you all on Thursday, but tomorrow I will have my regular office hours from 3 to 5, and Emma will have her regular ones in the morning. I'll be happy to answer any questions, but otherwise, you are free to go. Have a great week.
Thank you.
Thank you, bet.
Thank you.
I do have one question that I was wondering if you could maybe go back to.
Sure.
Okay, so it was one of like the short response ones. It was the one with like the water tank. I was just wondering if you could maybe explain why both of the pressures are 0.
See if I can get back to it. This is slow. The first one, right? With there it was. This one?
Yeah.
Okay, so so when you have the free jet at the end that's going back into the reservoir, of course that's atmospheric, right? But the other thing then, the pressure on the inside, Right here we say, assume that the pressure inside the tank is the same as atmospheric. And that's where the other one gets defined.
Okay, perfect. That makes
Yeah,
sense.
so that kind of language is really key in these.
Right,
kinds of
yeah,
questions.
because I with the first part, I think I might have just set my 0.2 at like an incorrect place or something, because I was getting a different pressure for that.
Well, you also may have had different numbers.
Okay, yeah.
Right, yeah, because I think there was another one, there was a version with 88, another one with
Yeah.
85, and so forth.
Okay,
So,
cool. All right, thank you.
you bet, no problem.
I had a question for the second full problem at the end.
The very last one?
Yeah, the very last problem, the very last part to it. So the integral that I usually see representing what like m.3 would be would be over the control surface, not the next problem after this one.
Oh, sorry, I didn't go far enough. I was like, what?
No, you're good.
Okay, sorry.
Yeah, so I'm used to that saying control surface instead of, or CS instead of system. Is that interchangeable?
Oh, I did not catch that until today. That was actually a typo in the definition. So thanks for bringing that up. That was supposed to be control surface. Let me look at the way I stated it. So I ran into a problem where this was also a graphic because I couldn't find a way in Canvas to basically put in an equation, right? And so what I ended up doing was typing all this out in PowerPoint, and then I took a screenshot. But I think what happened was, sorry, let me go back real quick. I got my eyes tested this morning, and apparently I need new glasses. I think what I did here was I copied. Note that the top one has that integral sys. I either copied that one and then tried to modify it for this one, but you're right. This should have been CS. Yeah. So my apologies if that threw you off when you were working this one out.
I approached it like it was a system. I was like, okay, well, you can't look at just 0.3 and have it be the whole system.
Okay. So you
I said it wasn't possible.
So you would have said, because okay, and that was thrown in as sort of that was a suggestion in Part D anyway. Yeah. Okay. Well, thanks, Louis. Let me just make a note real quick. Shoot. Let me do one thing here. Okay. Louis, for some reason your name isn't popping up. What's your last name?
Salvins. It always puts my middle name in. I don't know why. I can change it.
Okay, no worries. But can you spell that for me?
Salveson.
Okay, perfect. Yeah, let me take a look at that then, because that was definitely a mistake on my part. So
Okay.
thanks for that.
Yeah, no, I have a pretty detailed explanation of it, and it was rather confusing for me. But,
No, understandable. And that was, I did not notice that until today. I was sort of looking through going, where did that system come from? So yeah, thanks for that.
All right, thank you. Have a good one.
You too. Saeed, did you have a question? Or anyone left? Michael? Mohammed? Anyone? Okay, I guess not.
Professor, I had a question.
Oh, okay, yeah, Mohammed, go ahead.
Yeah. So about the final, is it going to be cumulative? Is it going to be like it's going to contain all the topics we had from the beginning of the test to the end?
Yeah, it will emphasize. So I haven't figured out the design exactly. I started to rough it out already, but it will emphasize what starting linear momentum. But it will include a little bit before that as well. So think about it this way. I think we're going to have like 4 long problems, and 2 of those would be from like linear momentum on, and 2 of them would come from previous. So you can imagine one from the kind of like the first midterm and one from the second midterm, 2 from everything since the second midterm.
Okay. And then it's going to be like 10 multiple choice and then 6 short answer and then 4 long answer. Is it going to be something like that, or is it just going to be
something like that? I haven't quite figured out. I think